start recording. Okay. All right. So I'm gonna do homework questions. Some homework questions. Section 24.5, page 748. Number 7. I can't do all of them. I can't do 3 questions. So we're going to choose from number 7 and 11. I will choose one, and I will do number 15. 2 questions I will do. Okay. Because the whole class will be over if we choose 3 questions. You understand? So I think from 7 and 11, they are of the same category. So I will do probably 11. The same function anyway. Number 7 and 11 are the same. They use the same function. So I would rather have 11 because they ask more questions in there. Number 11, but the function is the same. Y equal to 15 is the same. So I think let me do 15. Okay. What is it? Strawberry. Number 15 is number 7. Number 7. Number 11. Number 15 are the same question, except that number 15 is more. It has more questions to it, so you can sketch the graph. So I will pick number 15, which will cover 7 and 11. Okay. Number 15. It's saying use y equal to 2x cubed plus 3x squared minus 36x minus 10. Okay, so find first number 7 states find the increasing and decreasing. Number 7, find the intervals of increasing and decreasing. Which we're going to need anyway for sketching graph. Number 8, okay, no, number 11 rather. Number 11 says find the local point, find the local maxima and local minimum. Local maximum and minimum points. All right. Number 15, find the values of x which the function is concave up and concave down and any points of inflection. This is something we're going to do, okay? So now I get it. So I think I will do number 11, period. I won't do number 15 because we haven't covered it yet. So we're going to do, I'll give you definition and all that before I do example, okay? So I will do your number 15, strawberry, but you just have to wait for a little bit. Okay, so as part of number 7, we find dy by dx, which is equal to 6x squared plus 6x minus 36. And we said that the 0, it gives me critical numbers, okay? Then how do you find the critical numbers? You find the derivative, equate the 0, and then of course you can factor 6x squared plus x minus 6 equal to 0, and then you can factor x squared plus this part can be factored as x times x, and then 3 and minus 2, because 3x minus 2x is x, which is the middle term. So it works 6 into x plus 3, and then x minus 2 equal to 0. So therefore, x plus 3 equal to 0, x minus 2 equal to 0 is x equal to negative 3 and x equal to 2 are the critical numbers. Okay, so therefore now we're gonna split the critical numbers are x coordinates of the maximum and minimum points. You know what I mean? These are almost there for the maximum and minimum points, but that's number 11. But let's find the intervals of increasing and decreasing. So we do sign chart. Sign chart. How? Well, copy the derivative. Is there any question?
Yeah. So with that, in this case, the 3 and the -2 is interchangeable, right? Like it could be -3 and then 2, or it'd be -2 and +3.
No, it can't be. It is actually the way they are. You cannot have -2 as if you plug a -2 in here, it won't be 0. They're not interchangeable. The sign is not.
Okay, thanks.
Yeah, you understand what I mean? That what we're looking is for something for the derivative to be 0. For the if I plug -2 in this, I will never get 0. So it's not really a solution. So therefore, the only thing is x plus 3, x minus 2, and number 6 multiplied 3 of them is equal to 0. We know that 6 cannot be 0, but either x plus 3 equals 0 or x minus 2 is equal to 0. When I do that, what I get is x equal to -3 and x equal to +2. We cannot use x equal to +3, x equal to -2, and you can easily check that those are not the solution, because when you plug them into the derivative, which is right here, they will not give you 0. So they can't be a solution. For them to be a solution, they should satisfy the equation you're solving. And they don't satisfy. If you plug +3 here, +3 squared plus +3 is like 12 minus 6 is not 0. Can't be 0. So they cannot be anything else except -3 and +2. The chart, okay, is split to a few intervals. There is -3 as a boundary line. There is 2 as a boundary line. So any numbers below -3 and the numbers set between -3 and 2, which we write normally in math like that. Any number between -3 and 2 is -3 less than x less than 2. And any number beyond 2 is that. So therefore, the derivative, which is 6x squared plus 6x minus 36, you can take a value here in between less than -3, say -4, plug -4 here, 6 times 16 minus 24 minus 36. So 6 times 16 is 96 minus 24 minus 36. It's positive, right? So you get the same answer, positive. Thank you, Wissam. And then we're gonna check a number in between -3 and 2. It's 0 is better. I use 0, 0, 0, -36. So it's negative. So at x greater than 2, you can plug 3. So it is positive. 3 squared is 9 times 6 plus 6 times 3. It's way beyond -36. So it's positive, right?
Sir, I have one question. Whenever we get the first sign, and then the rest of the signs, they will be alternating, right? Because we are moving from...
Yes. Unfortunately, there are times where you have negative and negative, or positive and positive. When
Even
the
between the
when
roots?
the inflection point and the maximum minimum point is the same, then the sign doesn't change. So there are very rare cases that we cannot just say, oh, plus minus plus, or plus minus plus minus. Technically, every good graph should be like that. Do you understand, Wissam? There are cases that have had signs, even though they are passing a critical number, if that critical number happens to be an inflection point, which we're going to discuss, there is a chance that the sign doesn't change. because
Okay,
of the
can we
inflection.
have an example like that so we can like grasp
I
the
really
idea?
don't remember, but I have done it from experience. I tell you.
Okay, thank you.
Yeah, I remember I done it, and then there was no sign change because of the nature of the critical number, especially is a inflection point. But for all graphs, normal graphs, this is right. What you said is right. There is a pattern. Once you figure out the first interval is positive, the if this number 3 is a critical number, if this number 3 is a critical number, definitely this got to be negative. You got to change sign. That's what we're saying. So the slope changes from positive to negative, or the slope changes from negative to positive, right?
So in this
Technically,
case,
by that.
sir, in this case, we'll check our critical number from first derivative and the
Yes,
second derivative. If they are not equal, we can do that. If they are equal, we have to
yes,
find the sign.
yes, you're right. Yes. The only case, very rare case, it never happens, is what we have, what we're gonna say, this is called inflection point. So if you have X, if there is a graph like that, you know, so this point is called critical number. This point where the graph was at a tendency of going down, but at that point it behaved like going up. The graph wanted to be going up from that point. That point is called inflection point. That is what the number 15 Strawberry asked me to do is talking about. We haven't discussed that yet, so we will discuss after this example. Okay.
Okay, sir.
If that point and that point are the same point, this plus minus doesn't show, and that's very complex. Like I mean, that is very rare. It doesn't happen. But it is as a math person, I would say I don't want to say yes. It's always like this. You understand, Wisdom? There
Yes,
is
sir, it's
even
clear.
I have seen one where it doesn't follow the pattern. So I would say be careful. But most of the time, it is this pattern, right? Okay, so class, everybody, what he's talking about is like once he get the first interval as one sign, plus or minus, he can generate the other intervals without even checking. I wouldn't take a risk, but from all my experience, it's that pattern. He's right. He's right. So when the problem would have been if I had plus the first and then I got plus the second, then there is a sort of, or did I make a mistake? You should check it. You know what I mean? But quickly checking is better, I think. Okay, so this is what we got. So as you know, the slope is positive on this interval, slope is negative on this interval, positive on this interval. So this is the maximum point, this is the minimum point. The intervals now, intervals of increasing, which ones are? The ones with a positive slope. So it is x less than -3, it's increasing, and x greater than 2. The graph is increasing on those two intervals. You can write this as 2 infinity. You can write this as the -3 and infinity. No, negative infinity and -3. All right. So the interval decreasing, on the decreasing, the interval of decreasing is only when the slope is negative and it's attained at -3 less than x less than 2. Or in other words, in interval riding, -3 and 2. Okay. We don't want the critical numbers to be members. You see, this is called open interval. This is called closed interval. If the 2 and -3 are part of the interval, we close them. If 2 is not part of it and 3 is not, -3 is not, it's called open interval because we don't want to include the critical numbers as part of the increasing and decreasing intervals, as you can see, because the critical numbers are neither increasing nor decreasing. They are at a zero slope, okay? So therefore, this is number 7. This is the answer for number 7, right, from the chart. Number 11, the answer is which ones are local minimum, which are local maximum. Of course, at -3, it's maximum, right? Maximum. But I still have to find y. At positive 2, it's minimum, as you can see from here, because when passing positive 2 from left to right, the slope changes from minus to plus. So that is a first derivative test, right? First derivative test. Oh, thank you. Wasim has calculated it. It's 71 for the -3, and then for positive 2, it's -54. So these are the two. This is maximum, local maximum point. This is the local minimum point, right? This is number 11. That's why they are asking. Okay. Is it okay what I have done? Who asked me those questions? 7 and 11 is actually Eric. Eric, did you follow me? Hopefully. Or you have any questions? Follow-up questions?
Is it minus 54, sir?
Okay, I will do that. Yeah. Was there any other question?
Then number 7, when you did the points of or the increasing, it kind of looks like that's supposed to be a y value, but it's not, right? Is there a better way of writing that?
Which one?
Say decreasing -3, 2.
Decreasing, yeah, the interval of my writing -3 less than x less than positive 2, or the interval -3 2, 2 in brackets. Could you repeat the question then?
Yeah, like the brackets, that kind of looks like it's a y value, but it's not, right? You're just referring to the x.
Oh, yeah, you mean this one. Okay, very good. So, okay, because this is not a coordinate point. This is an interval, we call it. So interval. You're right. If you consider this a point, yes, it is x and y component. I'm not referring to I know I should explain that. So this is interval. This ordered pair could represent two things. If you're talking about intervals, like what we did, intervals here, then it is not the y value and the x value. No. If this is a point on the plane, -3 is for x and 2 is for y. So this is a point. You know what I mean? So it's an alternative way of representing intervals. If you don't like it, stick with this. Okay.
Okay, thanks for explaining.
I hope you understand. Yeah. I think the word interval should be accompanied by this kind of writing. Okay. To avoid confusion. Is that what you mean? The confusion was there because it looked like an ordered pair. Is that what I sensed?
Yeah, thanks.
Yeah, Eric. So yeah, I should mention interval or something, but when you put it in an ordered pair of numbers separated by comma, you're right. The first coordinate is x, the second coordinate is y. But if it's confusing, you should avoid it. Yeah. So these are like the coordinate points. So is -371 is a local maximum point, and then -54, yeah, 2 and -54 is a local minimum point. Okay. So anybody with any follow-up question on those? Are you okay with this so far? Finding the increasing, decreasing intervals, finding the local maximum and local minimum, because I'll ask you on the test, 100%. Okay. You gotta ask me otherwise. Oh, Sivan, you have was it 2 and -18, Sivan? Did we make mistake somewhere? Okay, thank you. All right. So now before I do number 15 as an example or as a part of the exercise, I'm going to do a subtopic which says inflection points, inflection points and secondary inflection points and second derivative test and second derivative test. So what is an inflection point? An inflection point actually is a point where the graph changes from concave up to concave down, or vice versa. You know. So I think that's good enough. An inflection point is an inflection point is a point where the curve changes from being concave up to concave down, or from concave down to concave up. So as an example of a drawing, so if you have like that, so this point, let me call it x1. Why am I interested? This point, let me call it x2. I am interested on those two because they are peak points. They are local maxima and local minimum, and they are called what? Note that x1, the x2 are called what? What did we call them? They were called critical numbers. What are critical numbers? The x coordinates of local maximum and local minimum and minimum. These are what we said. We've been doing that the last two classes. And now, note this is number 2, but this point, which is halfway here, maybe here, you know, here, this point is, let me call it x, my numbering was not x3. Okay, x3 is an inflection point. An inflection point. You know, you can see that because the tendency of the curve to go down, right, to go down is up to that point, and then it feels like it's trying to turn upward. So that point is inflection point, and it is very easily found in math. In mathematics, we can find, so how did I define it? An inflection point is a point where the curve changes from being concave up. It was concave up here. It's concave down. It changed from the tendency of concave up to concave down at this point. So that is inflection point, and vice versa. Okay. So x3 is an inflection point, but x1 and x2 are turning points. They are maximum and minimum points. I mean, x coordinates of those points. Okay, so how do we find an inflection point? How do we find an inflection point? Do you remember how did we find a critical number? How do we find an inflection point? Right? I just want to ask you, how did I find a critical number? How did we do we find
that derivative equals 0?
yes? How do we find critical number? F prime of x equals 0. Now, how do we find inflection point or inflection number? Let me call it, because the point will be yep. Maybe I have an answer. Second derivative equal to 0. Okay. So the second derivative f double prime of x equals to 0. Right. That's exactly what it is. Can you mute yourself, whoever, probably, or I can mute the whole class otherwise. Okay, thank you. All right. I don't know why this is happening. So second derivative equal to 0 is actually the way to find the inflection point and solve for x. That x will be inflection point. Okay, that is one thing. Now there is another test, what we call second derivative test. Second derivative test. This is an alternative way of the first derivative test. How do we find a critical number if it is first derivative is very easy. It's more like using sign chart. We said if this is a critical number, anything below x less than c, if the slope changes from plus to minus, and this is x greater than c, then if it's plus to minus, then c is maximum, we said. If it's a critical number here, x is less than c and x greater than c, the slope changes from, this is dy by dx. This is dy by dx. If the dy by dx changes from negative to plus, then it's going down and up, so it's minimum point. This critical number is a minimum point. That's why this is what? First derivative test, if you remember. That's what we did last class. Okay. Second derivative test is another alternative way of testing. Okay, another way of testing local minimum and maximum points is the second derivative test. It's very easy and it's very effective for polynomial functions. So what it does is, if you have a critical number, yes. So the second derivative. Oh, okay. I will correct that if I say so. Yeah. Thank you. So if okay, let me call it A. If A is a critical number, this is a critical number. It's not inflection number, mind you. The inflection has nothing to do with the testing because it's not a minimum or maximum point. This is critical number. How do we find it? We find it by f prime of A equal to 0, not f double prime. We find f prime of A is equal to 0 to find the critical number. What is the test? Okay, if you find the second derivative and you plug your critical number into the second derivative, if the sign is negative, if the sign of that number is negative, then it's maximum, local maximum point. Then x equal to A is local x coordinate of local maximum point. Or I could say A and some y is a local maximum point, So if f double prime, and if you plug it, if you have the second derivative, you plug your critical number and you get a positive sign, then ay is a local minimum point. Now I will do number 15, what Strawberry asked me to do as a homework to justify, or at least to give you a clue what I'm talking about for those two concepts. The two concepts are inflection point and then what is the second derivative test, right? So number 15 example. So we will do some questions on
sir, should be like the f double prime a equals 0, and
no, that is for critical number. For inflection point, Wasim. That is for inflection point.
I mean, on the chart, is it for inflection point? The fa equals 0?
This is for critical number. No, the chart is for critical number, and the test
but
is
we find
an alternative way of.
Do we find the critical number by for inflection, we find the critical number by equating the second derivative to 0?
No, don't mix the words. Be careful. What we call critical number is only if you use f prime, not f double prime. What we call the inflection point is when we use f double prime.
But here, like, we used both of them. We put a, like we are mixing them.
A critical number, to emphasize a critical number, I use that. Nothing. This has nothing to do with the test. But you know that a critical number, if we call it critical, the derivative, if you plug it on the derivative, it becomes 0. That's what it is. This is a test. And then ask me now.
Yeah. Okay. And the test we do, like, do you agree with me? Like, the critical number for inflection point is different than the first derivative, right? Each one of them has its own. So in this case, we need also to find another critical number for f double prime equals 0, right? It's another critical number.
No, I mean, we don't need it. We are testing the critical number. We don't need f double prime of 0, f double prime of x equal to 0. We don't, unless we are asked for inflection point.
Yeah, this is not for inflection point. I thought it's for inflection point. That's why. Okay.
No, it is critical number we're testing on the second derivative test.
Okay, sir. Okay, thank you.
Okay, no problem, Wasim. I wanna emphasize, when you're testing local minimum, local maximum, we only test critical numbers, which is the number we get from the first derivative. I think the category came, unfortunately, I am talking about inflection point and then talk about second derivative test. It kind of senses that it is mixed up, but the second derivative test has nothing to do with the inflection point. Okay, so what I mean is, on the second derivative test, I am still testing an alternative way of testing local minima and local maxima. So if I am testing local minima, which one is local min, which one is local max, I am still testing whether the critical number is local minimum or local maximum, not the inflection point. Wissam, you're not happy about that explanation?
No, because there will be too many criteria. Like, the first test is not enough for local maxima.
Oh, yeah. It's not enough, because for trigonometric functions, listen, for trigonometric functions, most of the transcendental, when we use transcendental functions like logarithms, exponential functions, trigonometric function, we use first derivative test because it's very easy to plug numbers in. But for polynomials, because it's very easy to find the second derivative, we prefer the second derivative test. They have their own advantages according to the nature of the function you're testing. You understand? So
Oh, yeah,
the
it's
book
easier
cover,
for some.
okay, yeah. So the book cover both of the tests. As students, we learn the tests, and then when we use them, we use them. It's just the fact that mixing up the inflection point with the testing is not right. That's what I'm trying to say. It might confuse you. The inflection points are simply you find the second derivative, you let it to zero, you find your inflection point, the x component of the inflection point. Then the business is done. I'm not testing the inflection point. I'm testing the well. If you're talking about local, I mean, what do you call uh, concave up, concave down? That is another test. A graph
But,
is
but
concave. I will define that in a minute.
okay.
Okay. So number example 7, page 748, number 15, for example. So the question is, y is given the same 2x cubed plus 3x squared minus 36x minus 10. So they want to know, we did increasing and decreasing. We did critical numbers. Now they're asking find the inflection points. I will ask you find the critical numbers. Even though we did it, critical numbers. Second, find the inflection numbers. Remember, I call inflection numbers. The book doesn't. I call inflection numbers the ones which are x coordinates of inflection point, x coordinates of inflection points. Okay. The third case is, okay, if you find the critical numbers and then check or test the critical numbers using the second derivative test. Before we use the first derivative, using the second derivative test, for local max and local min. Okay, we're going to do this. I can't write when it's close to the, okay. So I hope you understand the question. So solution, first of all, is just like a summary, but we're using for testing a different test. So we have the first derivative equal to 0 will give me critical numbers. This is a principle what we have found. When the slope equal to 0, then we have a horizontal tangent, right? So what is the derivative? It is 6x squared plus 6x minus 36 equal to 0. And we factored this as x plus 3 and x minus 2 equals 0, then x equal to negative 3, x equal to 2, where the critical numbers. Isn't that what we have in question number 7? Yeah, here, minus 3 and minus positive 2. Okay, these are my critical numbers, all right? So I'm going to also find, they ask me, these are critical numbers. Now, before I do test them, they unfortunately I wrote it in such a way. So I will go find the inflection point. The inflection point is, the inflection number is simply just the same. So find the second derivative and let it to 0. It will give you a number. That number is inflection number. So, and what is the second derivative of this? Which is 12x plus 6 equal to 0. So if you solve for x, then 12x equal to negative 6, x equal to negative half. So x equal to negative half is called inflection number, or This is inflection number, is an inflection number, or the inflection number of the graph. But better, we want to do negative half. And what is y? Y is, you remember y, or well, we can find y by plugging x equal to -1/2 in y equal to the original function. I'm sure Wasim helped me, Wissam helped me. 2x cubed 3x squared, 2x cubed plus 3x squared, okay, minus 36x minus 10, okay? So yes, thank you so much. 8.5, he found it, 8.5. So first of all, I want to ask the class, did you know how to find the inflection number? All you got to do is find the second derivative, equate it to 0. Okay, second derivative of this is 12x plus 6. And then when you equate it to 0, you solve for x, and then you get 0.5, negative 0.5. And that's what we got. Well, you can make it 0.5 if we want. This is the inflection point. Understand? All right. Now the third part of the question is use second derivative test to check x equal to -3 and x equal to 2, because these are the two critical numbers. These are the two critical numbers. I want to check which one of them is my local maximum, which one of them is local minimum. Okay, and I'm going to use a second derivative test. So for x equal to -3, I could say -3. This is my test. What is f double prime of -3? What is the value or the sign when -3 is plugged in into the second derivative? Where is the second derivative? The second derivative is this, 12x plus 6. Second derivative, dy squared y by dx squared is what? 12x plus 6. 12x plus 6. So what happens if you plug -3 in it? It's negative. Okay? So 12x plus 6, when you plug -3 in there, it's -36 plus 6, it's -30. It's negative. Then if the critical number is inserted into the second derivative and the sign of the second derivative is negative, then this -3 and what y value is what? A maximum or a minimum? What was the second derivative test say? It's kind of the opposite. If you get negative, that point is a maximum point. Sorry. Maximum, yes. So a maximum point. Okay, so we can figure out what is the y value at -3. You plug the y value at -3, so you plug the function -3 in there. You found it, my friend Wissam? It's been helpful. Okay. It is 71. Very good. So 71 is what it is. So now let's check if x equal to positive 2. What is the status? Is it? It's obviously minimum point, but let's double check. So f of double prime of 2 is what? F double prime of 2 is, this is the second derivative. 12 times 2 is 24 plus 6 is 30. So it's positive. Yeah, it's positive. So therefore 2 and, yes, what is the value of y at 2? Arthan, at 2 we found -54, right? Yeah, thank you so much, Arthan. At 2 and -54, this is what? If the second derivative of a critical number is positive, then that point is a minimum point, a local minimum point. Yeah, this is a general rule of second derivative test. But what we did last time was first derivative test was different. This is the second derivative test. I don't want to mix up. I don't want to confuse you. But you could have done this. Oh, this is -3 here. This is, we did this in number 7. You see, what did we found? Number 11 at least. Number 11, is it consistent what we have done? So -3 and 71 is maximum point, 2n minus 54, and but we used first the sign chart, the first derivative test. You understand? First derivative test is used when we found that -371 is local maximum, 2n -54 was local minimum, which is consistent with the second derivative test, right? -371 is maximum point, 2 and -54 is minimum point. Okay, I don't have to do it again. But there are two alternatives for you to double check whether a critical number is a positive, minimum or maximum. Very good. So this is for testing. And number 15, they are only asking that. The second definition is local maxima and local minima. When is a graph local non-local maxima, local minima? The second definition I want to use, the second derivative, is for concave up and concave down. Okay, so a graph is concave up when the second derivative, so concave up and concave down. So this is how we do it. If the second derivative of x, this is not a critical, neither critical nor inflection. If the second derivative of x is positive, it is f of x. You make a conclusion. This is conclusion, but you use second derivative test. You use second derivative. Your conclusion is about the function f of x. So f double prime of x is greater than 0, then f of x is concave up. If the second derivative is less than 0, then f of x is concave down. This is another taste of concave up and concave down. This is additional knowledge. Say for the example we had, example on number 15 above. When is the graph concave up or concave down? Where? Okay. What do we tell? Can you tell me what we could do?
At the inflection point. We tested at the inflection point.
Yes. Yeah, definitely. But then we don't involve inflection point to check whether it's to find the interval of concave up or concave down. We don't.
So it's before and after.
Yes, exactly. So what would you do? You find the second derivative and solve for greater than 0, right? So what is my second derivative for the above question number 15? You're right. It's before. It's greater than or less than the inflection point all the time. It comes to be. But what is the second derivative? We find the second derivative to be this one, 12x plus 6. So you should say 12x plus 6, which is f double prime of x, is greater than 0. You solve that inequality. So 12x is greater than -6. X is greater than -6 over 12. X is greater than -half. So the interval of concave up is from -half up to infinity. Or this. This is interval of concave up. The graph is concave up for all values in the interval. Okay. So if you solve also similarly, if you solve 12x plus 6 less than 0, I know we have found the inflection point. We could have said less than, greater than, because we have already the chart. But if we have many inflection points, it's good to find it like this: 12x less than -6. We could have just done it by x is less than -half. So is the interval of the graph the interval of the graph for so the interval of the graph so we can sketch now. Can we sketch the curve?
Sir, I have one question. Now we say
Yeah,
that if double prime x should be larger than 0, right?
yes.
And here we have the separation is -half. So
Yes.
still we have some values they are less than 0, and the concave.
No.
Yeah.
Well,
If
yeah,
you
yeah. At this -1/2, these are
yeah.
anything beyond this will be going up, kind of, and then anything in here are going down, kind of.
Okay,
Okay.
so if you go to the definitions here on the table, that it's
Yeah.
up. If you go up a little bit
Mm-hmm.
more, yes, here, sir,
Okay.
on this table, sir. See if it's larger than 0, and should it be larger than the critical,
No.
which is -half?
No. It is larger than 0, but the system will produce an interval. The inequality, this inequality will produce an interval out of that. It's not,
Oh,
the second derivative is not, that's not the definition. The second derivative greater than the inflection point, the second derivative less than the inflection point is not a definition. The definition is a graph will attain a concave up status only when the second derivative is greater than 0. And you solve for x. This is what we
okay,
do.
okay.
You
I
understand?
got, yeah.
So
Yes,
the
sir, yes.
inflection point has nothing to do with there. It will produce,
Yeah,
the inflection point will pop up after you solving it.
yeah, and other means -half is actually making the second derivative 0. That okay, I got it.
Oh yeah, definitely. That's how we found -half. Remember the inflection point in question number 2? We found the second derivative equal to 0. So that
Yeah, I
is
was
kind of,
comparing numbers and not the definition. Okay.
yes,
Yeah.
exactly. So when we have the definition, it's greater than or less than 0 on the definition. Oh no, on the concave up, concave down. Every time you find the second derivative, you set it to greater than 0, then you will get interval of concave up. You understand? Hopefully.
Yes, sir. Yeah.
Yeah. Okay. Very good. But the result will bring you to -half still, because it's at the -half, which is a boundary line for concave up, concave down. What is the boundary of the critical number? What is the boundary of what? Critical number is a boundary of what? Increasing and decreasing of the curve. You understand? But inflection point is a boundary of concave up, concave down. Okay. So I know you could do it again. And so what is a graph look like? Almost done. We're done actually. So what critical numbers? There are 2 and -3. So 1, 2, 3, 4, -1, -2, -3, -4. So I have 2 here. I have -3. What is the y values? What are the y values for the critical numbers? They were big numbers, are they?
71 and minus 54.
Oh, they're huge. But I can cheat. Like I say, this is 71. Here is negative 54. So at 2, what do we have, class? At 2, we get what?
Minus 54.
Minus 54. Thank you. At 2, we got negative 54. And that point was point of what? Maxima or minima?
Minima.
Is that minimum? Yes, thank you. So it's gonna turn up like that, right? So at negative 3 and it is 71, it's maximum. At negative 3 and 71, it is maximum, and then it's gonna go like that. So where is the inflection point? Where is the tendency of going down gonna change? Start changing. The tendency of going down, it starts changing to the tendency of going up. At what point? At negative half, was it?
Yes.
At negative half, right here. Negative 1 over 2.
And 8.
And then the y value is?
8.5.
Yes, 8.5, somewhere here. So it is going down up to this level, but it just shows a tendency of going up at that level. Okay, it's the tendency that we are, the inflection points are showing. Yeah, I had it the better way the first time. Okay. So this is going up, going down because it's maximum, minimum, and inflection point. I think we should do, what else do we need to do? This is section 24.6, x-intercepts. We should find x-intercepts to complete this job, right? How do you find x-intercepts?
It should be Newton method. It's very
okay, Newton's method, but we can use it straightforward. Y equals 0, right? Y equals 0.
This is, I think, one of the difficult polynomials that they don't have.
Yeah. Oh, you can.
Extensions.
2x cubed plus 3x squared minus 36x minus 10 equal to 0. Yeah, okay. I think they wouldn't give us a difficult one. So technically I have to stop here because I don't have time. But really, 2x cubed, 3x squared, 2x cubed minus 3x squared, plus minus 36 minus 10. That's what we have to solve. So yeah, minus 36 minus 10. Okay, so is it really like a 2 at 3? Yeah, probably you're right. So we probably have, if we don't know, by plugging, we can see that at 0, so at maybe at 3, for x equals 3, let's check. For x equal to negative 4, both of them. Is it 0? That's how we check, because is it going, yeah? Yeah, okay, thank you. You're right. So that's why they didn't ask to sketch maybe, but that is the best we can do. If I ask you a question like this on the test, and then I ask you to sketch, this sketch is good enough. All the information indicate that it's concave up. Where is concave up, concave down intervals? Yeah, so it's concave up to the right of negative half, concave down, concave down to the left of negative half. It's increasing between negative 3 and 2. I mean, that's decreasing and increasing of negative 3 to the left and of positive 2 to the right. And then I know it's going like that, but you don't have to because you don't know the x-intercepts. So either find another point somewhere here by plugging. Say you can find by plugging the number 3 or number 3 or number 4, you probably get a positive number. Then you can complete the curve, or for x-intercepts, you don't have to use You don't have to use what I say, Newton's method in the test. All I need is, this is a good sketch of curve. You don't have to complete it because the x-intercepts are not that easy. Okay, I don't want to keep you late. I think we spent enough time for homework questions. That's why we're a little bit behind. I will stop recording here, and then we can talk for a little bit if you want.